So at the beginning of each class, I'll kind of do some quick reminders of X, Y, Z logistics things. So to that end, remember to do the financial aid thing, just that quick survey. Make certain you get that done by tomorrow. Takes no time whatsoever, but just need to get it done so you all can make certain that your financial aid isn't delayed, and it does count as one of our quizzes in the class, so 3 points. Also, discussions start this coming week, so not today, but this coming week. To clarify, I always like to say the dates. The 13th through the 17th is when discussions are starting, aka this coming week. So keep those in mind. I did also realize someone had sent me an email and pointed out that the dates weren't quite correct on the assignment, so I've gone through and those should all be corrected now. I had imported the course over and it didn't quite line up because the hurricane ruined everything and the spring break and all that jazz. So I've adjusted some of the due dates for assignments that are like, these were like assignments weeks from now. So there's nothing that affects it, but it should all be good now. And I'll double check that soon as well to make sure that's good. But our goal today is to learn about vectors, units and vectors, and to get as much of this as we can. We probably won't quite finish this entire PowerPoint, but we'll get pretty darn close. Any little bit of leftover we'll kind of roll over, but I should be able to at least cover all the ideas. We might just not be able to do the couple practice problems at the end as much in detail as I'd like. Just a little tight, but we'll do what we can. Vectors are something, so it's an arrow. These arrows are what we're going to be working with. And I think I might have mentioned them a little bit last time. I'm not sure how much I got into them. But we'll get to them today on some level. And yeah, be a good time. So math skills, algebra, and trigonometry. Today I'm going to try to show you where trigonometry is going to show up in this class. And when I say the word trigonometry, you just need to be comfortable with right triangles. That's trigonometry is the study of right triangles. So in this class, something that's going to happen again and again and again and again and again, you're going to have a vector. You're going to have something that has a size and a direction. And just foreshadowing, you're going to have to turn it into a right triangle. And we'll do that. And so can you take a side of a triangle and an angle and find the other two sides? Can you take two sides of a triangle and find the third side? That's the math skills I'm talking about. Algebra up here, can you rearrange an equation to solve for a missing variable? That's going to happen all the time. It's not super common for the equation. So remember, there's that big bank of equations in the formula sheet. The reality is you're going to very much have to do algebra in pretty much the vast majority of problems. You have like less than a 50% chance of an equation being set up in a way that already works for you. And the reason for that is the equation, it's just instead of having to write the equation 5 different ways, you write it one way and then you can rearrange it to suit your needs. So the problem-solving strategy is something you're also going to use in much of this class. You're going to hear me say this again and again and again and again and again. And anytime I solve a problem, I'll go through this process. This is how you solve any problem in life. This is how you make any decision, whether you realize it or not. This is kind of what you're doing. Draw a picture if possible. Okay, that might vary. But in physics, you're always going to want to draw a picture, because if you can't visualize what's going on, then you're going to have a hard time solving it correctly. So you're going to see that as we solve problems. A picture is wonderful. It helps us organize information. It helps us predict what's going to happen nice and easy. If your picture is bad, the rest of the problem will go bad. If you're visualizing the problem wrong, the rest of it's going to go south. So that step is really, 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 really valuable. All of these steps are ones that, these aren't steps for beginners. These are the steps that experts follow. Like, this is the process that people follow to solve problems. So I'm not giving you all this and then you'll graduate one day from using these steps. No, this is always the process you're going to follow. It really just comes down to how much of this you're going to write on your paper is what might change as time goes on. But you're always going to go through this process. And the more you write on your paper, the less likely you are to make a mistake. When you write the number 3 on a piece of paper, it will stay the number 3 for a very long time until that paper degrades into nothingness. If you try to remember the number 3, your memory is far more temporary than what you write down. So the more you try to hold in your head, the more mistakes you'll make. Be prepared for that. It'll happen. You'll see what I mean one day. I mean, yeah, it's probably already happened to you. If you didn't write something down, you forgot about it. or you forgot something you didn't remember accurately. All right, so draw a picture. Identify what's given in the problem. Identify what you're solving for, step 2. If you don't know what you're solving for, then you have no idea what to do. Like, that's hopefully obvious. Step 3, find the equation or processes that let you process the givens to get what you need, and then do it. Again, this is the process for anything you do in life. You want to vote for someone? First, you identify all the information out there about all the different candidates. Step 2, what are you deciding? Who to vote for. Step 3, take all that information that you know, process it with the values and beliefs that you have, and then do it and make a decision to vote for someone. You're on a deserted island and you're trying to survive. Step 1, take stock of all the materials you have. Step 2, what do you need? Food, shelter, those kind of things. Step 3, figure out how to take what you have and get what you need. This is how you solve problems. And this is what I hope to teach you all. This is the most important thing in the entire class. The content, if you forget it all, whatever. But if I can teach you to be a better thinker, that's going to help you way more. And that's what I learned as a physics major. So great. That's a thing. We're going to use that again and again and again. And you are literally going to see me when I solve problems. Number it. Step 1, step 2, step 3, step 4. I, in class, will write down all these steps, and I'll write it really in detail. You decide how much you want to write. But when you're solving a problem, the worst thing you can have is just a blank paper. If you're solving a problem and you're stumped, don't leave your paper blank. Start trying to draw a picture. Start trying to write your givens. As you start to go through this process, it's going to help get things moving. Don't leave your paper blank. That's because when people are trying to solve a problem, I literally will just say these out loud. All right, what's given? All right, what are we solving for? You can ask yourself those questions. All right, here's a question for you to think about. You can chat with it with other people. So think about it for 10 seconds. What is 3? Not what is problems, not what is the third step in the problem-solving process. I know people like lean to that. What is 3? All right, talk to your neighbor. Tell them what 3 is. All right, what is it? What is 3? Who's got some confidence? I'm not looking for a specific answer here. What's 3? Yeah. A magnitude, okay. What else? Magnitude of what? That's a good question. All right, what else? What are some other ideas of what 3 is? You've seen the number 3 before. Yeah. It's a whole number. Good. All right, great. What else? Someone came up to you and said, you're talking to an elementary school kid, like, I got a 2-year-old, 3-year-old, she's asking why? Who else? What's 3? You've been seeing it your whole life. What is it?
Odd, not even.
It's odd, all right, great.
It's an integer.
It's an integer, great. If I told you I had 3, what's your immediate question?
2.
Yeah, that's the same in this class. So, in math classes, 3 was a number. It represented nothing. It represents anything. What the heck is 3? In this class, our numbers mean something. 3 what? And those are units. So in this class, every single time we have a number, there'll be something after it. And that thing after it tells us what it is. So 3 meters tells you how far you are from something. 3 meters per second tells you how fast you're going. 3 newtons is force. So units are what we put after a number to make it mean something. Without a unit, what the heck is 3? Like, it's an idea. 3 something. But it can be 3 anything. So in this class, we're going to see a bunch of different units. Don't forget them. But they also are a tool for you when you're solving problems and you're trying to identify the givens. The units tell you what they are. Anytime you see meters, that's measuring a distance. Now, there's lots of variables that represent distance. We'll see that. But you know it's a distance of some sort. When you see meters per second, it's always velocity. When you see newtons, it's always force. The unit always tells you what it is. And it always matches the same thing. And it's great. Now, there's this big SI table here of all these different unit conversions. You do not need to know gigameters. So let me zoom in on this because it's kind of hard to see. Basically, if you haven't heard of the unit conversion, the prefix before, you're not going to need to bother with it. I don't care about giga. Mega, maybe, but probably not. I'll leave it there. Kilo, yes, you're going to need to know kilo. Hecto, don't worry about it. Deca, don't worry about it. Dessa, don't worry about it. Centa, Milla, hopefully you've heard those before. They are relevant. Micro and nano, you're not going to need to worry about in this class, but in physics 2, they're very important because physics 2 is a bunch of small things. So we'll leave that there. And pico, maybe we can make the argument of leaving that for physics 2 as well. So units and then how to convert units is going to be a really big thing. And before I get more into this, I want to prove to y'all why they're important. Why is the metric system the best system? You have 30 seconds to solve this. How many inches away is your home? See if you can figure it out. Don't look it up. Defeats the purpose. How many inches away is your home from here? Oh, and no calculators either. All right, so I can almost guarantee you don't know the answer to this off the top of your head. Like, if you do, that's interesting. I don't. I have no idea. I mean, I asked this question every semester. I have no idea how far away my house is in inches. You probably know something about how far. You probably know roughly how many miles your house is from here, though. So, let's just say your house is, I don't know, my house, maybe it's 5 miles-ish. I don't know for sure, but I'm going to say 5. Roughly, approximately. Great. All right, what am I going to do with this? 5 miles. What do I do from here? Convert it. How am I going to convert this to inches? Feet? How many feet are there in a mile? If you knew that, kudos to you. It's a weird number. I was like, if you didn't know that, that's fine. You don't need to know it for this class. It's not a nice... So there is 5,200 feet per mile. Great. That's going to cancel out the miles for us. We're not in inches yet. What's the next thing we're going to have to do? We're going to need to convert it to inches. There's 12 inches in a foot. So that's going to get rid of our feet. And great. There's our answer. If you can do this in your head, kudos to you as well. I can't. It's a number. Definitely a number. 5 times 5,000 is going to be about 25,000. Times 12 is going to be... Not 25,000, 2,000. Yeah, no, 25,000. See, it's awful. I'm not going to spend the time and energy on this. It's terrible. You use a calculator for this. But man, look how much work this takes to get a number that's absolutely disgusting at the end of the day. The metric system is so good. So good. So the metric system, instead, let's change this. How many centimeters away is your home from here? So similar question. Now, I will say the caveat is you probably don't know how many kilometers. If you lived in any country other than the U.S., there's only 3 countries that use the imperial system. That's the whole inches, feet thing. Maybe there's 4, but the U.S., and does anyone know the other countries that use it? They're not ones that you're probably... One starts with an M. Yeah, Myanmar is one of them, and then the other country starts with an L. Liberia. And there might be one more, I'm not quite sure. Those are the only countries in the world that use the imperial system. Everyone else uses metric because it's so much easier to work with. Unfortunately, for the U.S. to switch to the metric system, think of every single sign that said miles per hour. They'd have to change that. Every single sign that said miles, they'd have to change that. The cost would be insane. So it's probably never going to happen because that's a lot of dollars that most people don't care about. But in our class, we're going to use the metric system. It is the unit, the system used in sciences across the board. Unfortunately, well, you don't spare this. Engineers have to actually work in both. Engineers have to know the imperial and the metric system because depending on the different countries they work with and things like that. Anyway, looking at this, so if we lived in a country like Canada, Britain, Germany, anywhere else in the world, you would probably know how many kilometers away your house is. The unit conversion... miles, I think it's like 0.625 kilometers per mile, something like that. No, there's 0.625 miles per kilometer. Whatever, it doesn't matter. Let's pretend like it's 7 kilometers. So how do you go from kilometers to centimeters? So the way I do unit conversions, I don't have kilometers to centimeters memorized. I don't have that memorized. but I do know that there is 1,000 meters in a kilometer. And then I know, and I'm going to write this down and then I'm going to quickly erase it because this isn't actually how I do it. And then I know that there's 100 centimeters in a meter. So this is valid. This will get you the answer. Still some math involved. The math here is simple though. All we do is take the 7 and we count how many zeros there are. 1, 2, 3, 4, 5. And that's how many centimeters, and it's great. So this is one way of doing it. This is a common way. It's where you can cancel out the things. I'll now show you what I do. And my way isn't necessarily better. It's just what I prefer. I know that to go from 7 kilometers to meters, I chuck a times 10 to the 3 after it. So this notation here is how I write scientific notation. It's how you're going to see me write it. It's how your calculators tend to write it. This is the exact same as 7 times 10 to the 3. Same exact thing. And to clarify here, this is how many meters I have. So you're going to see me in this class use this notation of 7e3. There's a few reasons I do it. 1, it's slightly less writing than times 10 to the 3, so it's a little bit quicker. 2, I don't have to do superscripts, which are a pain to format on various things. And the third reason I like to use this E notation, this capital E, is it's really common for your calculator to use that notation. So your calculator, when you're doing scientific notation, if you want to write 7 times 10 to the 3, you often hit 7 and then there's a button with an E on it. It's either a capital E or it says EXP, and then you put a 3 after it. This is how you'll type it into the calculator. So it's just better in all the ways than times 10. It's what your calculator does. It's shorter. I love it. I don't have to format as many things. But you do you. When you're doing stuff, you can write 7 times 10 to the 3 or 7e3. It all works out the same. Great. So I know that to go from kilometers to meters, I multiply by 1,000. I just put E3 after it. Super, super nice. And then to go from meters into, let me get rid of that. To go from meters to centimeters, all I do is I add an additional 2 to that. So I multiply it by another 100. I add 2 to that. So let me just kind of put this up here. 1 kilometer, kilo equals 1 E3 meter. 1 centimeter equals 1 E minus 2 meters. 1 millimeter is 1 E minus 3 meters. So this is what I have memorized in my head, how to get to the base unit. And then I just reference this. Now in this case, I'm going from meters to centimeters. So instead of E to the minus 2, it's E to the positive 2. I'll just show you that on this right side. So 1 meter equals 1 E2 centimeter. 1 meter equals 1 E3 millimeter. 1 meter equals 1 E minus 3. So you can see when you go backwards, you just change the sign from a positive to a negative. And this is just telling you how many places to hop the decimal place. Multiplying by 10 is just hopping the decimal place in various directions. So 7E5 is just going 1, 2, 3, 4, 5. That's too many hops. 1, 2, 3, 4, 5. And we get the exact same answer we did on the top one. So unit conversions, hopefully you've seen these before. I'm doing a really quick overview of it. I'm not going to give you these in a test, but if you're worried about forgetting them, put them on your note card. They are things that you need to know. They're pretty easy to remember, in my opinion, because you're going to use them so many times, you'll secretly memorize it, but you can also put it on your note card. I don't care about memorization. I don't care if you have this memorized. I just care whether you can do it. We have to put things in base units whenever you all are doing equations in this class. Our equations are like machines. Equations are machines that you put stuff in, the machine churns, and it spits out some result. These machines are tuned for specific things, specifically in the base units. If you try to use the machine with the wrong inputs, like you try to put centimeters in them, or you try to put kilometers in them, it's not going to get you the right answer because they're not tuned for those units. They're tuned for base units. So you'll see, I'll point that out when we get to problems with those. And we'll talk about what the base units are. Rule of thumb, the base unit is a single letter. So like meters, newtons, It's just a single letter. The exception to that is the kilogram is a base unit for mass. And I don't know why it's not the gram, but it is what it is. Kilogram is the only unit I'm aware of where the base unit has a prefix. It's weird stuff, but anyway. All right, great. So nice. Hop the decimal place. Takes 10 seconds. So good. Way better than the imperial system. That's fine if you don't believe me. All right. So we're going to use length, mass, and time a lot in this class. We'll find some other ones in physics too. You'll learn about ampere. Don't worry about this for now. As I introduce measurements, I'll tell you the base unit and all that jazz. So this is just a foreshadowing. All right. Go ahead and try this out. So this is where I'm going to start to try Top Hat. Top Hat is not going to be a part of your course grade until next Thursday. So I'm giving you all today and Tuesday to get signed up, and then we're going to be using it and making certain it works the way it's intended to work and all the good things and that you're registered and yada, yada, yada. But sign up before, yeah.
So on that, in your announcement, you said that we could go to the UCF bookstore right there in the plaza. I went there and they said they have nothing to sell us.
Okay, so just go up to the Top Hat website.
Okay, just wanted to
yeah,
get that out there.
Yeah, no, I appreciate you letting me know that. Yeah, that, I'm not going to lie, that a thing I sent with the whole how to enroll in Top Hat, that was sent by the people from Top Hat, so I trusted that that was accurate. Okay. But I guess not. But yeah, thank you for letting me know. Yeah, you can, I don't know why that happened. Yeah, but you can do it online, and that should work. My first class it was working for, so hopefully it works for you all as well. But yeah, here's how it's going to look. Sometimes I'll have questions already kind of in Top Hat. For now, I'm just using their quick little, hey, ask a question. What it's going to do is when I hit this, it will send a screenshot to your devices of this with the question, which is nice. Moving forward, I might try to use their integrated thing, but then I have to upload the PowerPoints. It's something I'm going to try. I just haven't gotten around to it yet. But for now, this will, if nothing else, make certain it works, and you'll see what it looks like and how to respond and all that goodness. The reason I use this is there's 100 people in here, and there is no, I could ask a question, and maybe 5 to 10 people will like nod their head or stuff like that, or things like that. That rules out the other 90, 95 students. This gives me a sense of whether it's making sense to all of you. So I ask these questions a lot. You can almost guarantee at least 5 of these questions each class, 5 to 10 of questions throughout the class where I'm asking you things, having you think about it. So this question, what is 38 kilometers in meters? Is it 38 times 10 to the 3 meters, 38.83 meters, 38,000 meters, or 3.884 meters? And a reminder, as long as you're answering, you're getting all the points. Anytime you get the question right, that's bonus points. 80% of the credit's just from doing it, and I only graded out of 80%. Anything extra is bonus. All right, I'll wait 30 more seconds. All right, and I'll close this out in 5, 4, 3, 2, 1. One of the things I'm hoping to use this for, one of the reasons I'm using it over iClicker, is what I used previously, is it has a thing where it can make questions for me based on the slides. So I make a bunch of questions, but this seems like it might be useful for making more questions. It's always nice to give students more practice. Not required practice, but practice that can exist to help you prepare for exams and things. So we're going to see how that works out the way I hope it does. Anyway, all right, what's the answer here? 38. So remember the unit conversion. To go from my way of doing it is I just chuck an E3. To go from kilometers to meters, chuck an E3 at the end of it, and great. Okay, so this answer's right. But remember I told you all that 38 E3 is the exact same thing as 38 times 10 to the 3. So that's also correct. If we actually write this out, it's 38,000. We move the decimal place 3 times. So that one's also right. And 38E3 is the exact same as 3.8 E4. It's just how many places you hop the decimal place. That's all the same. So they're all correct. How nice, right? We love that. This will happen every now and then. We'll have a question with multiple answers. And the purpose of this is as follows. On a free response question, if you gave me any of these answers, it'd be good. However, if it's a multiple choice question, the answer's only going to look like one of these, and I need you to know that all four of these are the same. I need you to be able to take an answer that your calculator might spit out. Maybe your calculator spits out 38,000, but on the test I wrote 3.8 E4. If you don't know that they're the same thing, you're going to have a hard time picking the right answer. So that's the reason for this question, so that it makes sense to y'all. No, and I forgot to say which one's right, so I'll go back and fix that. So that's the reason for this. It's a skill. It's a very important skill. We're not going to spend too much time on it today, but it is something I want to mention. You're going to use it a lot in this class. All right, not going to bother with that. Sure, I'll solve this one real quick. So these problems, whenever I have a problem like this that's like worked out, this is from the problem sets. So this is from those. So a car is traveling at a speed of 120 kilometers per hour. What is its speed in meters per second? So step 0, I suppose, is draw a picture. In this case, it's maybe not necessary, but there it is. Wow. All right. Step 1, what's given? So when we write down our givens, we like to write them in terms of our variables. Now, I haven't taught you any variables yet, so that makes this a little tricky, but we're just going to call it S for speed. It's a little silly for now, but in the future, it's just good to kind of get in the practice of this. So it's great. That's our speed. We want our speed in meters per second equals question mark. And then the question is, how do we do this? So I'm going to do it. I'm going to write down my relationships. I know that 1 kilometer equals 1 E3 meters. I know that 1 hour has 60 minutes. Has 60 times 60 seconds. 60 minutes in an hour, 60 seconds in a minute. So to go from hours to seconds, I'm going to multiply it by 60 and then by 60 again, i.e. there's 3,600 seconds in 1 hour. So using all that information, I'm going to apply that here. I'm going to take my 120 and I'm going to convert that. So I'm going to write this out the way that I think I've seen the most people do it in, and therefore the way I hope makes the most sense. We're going to do the 120. There is 120 times, yeah, that's how I'm going to do it, times 1,000 meters per kilometer. This seems to be the most comfortable way for people to do this, so I'm going to stick with that. And then we're going to multiply that by, for every 1 hour, there's 3,600 seconds. And so that's going to cancel out the hours. So by writing it this way, you can make certain you do the conversions in the right order. The most common mistake people make is whether to divide or multiply. So they might accidentally divide by 1,000, or they might accidentally multiply by 3,600. And the key to making the right decision here, and it's going to sound stupid, is saying what makes sense. Again, that sounds really stupid. But think about this problem. 120 kilometers per hour. What does that mean? It means in 1 hour, I travel 120 kilometers. That is what kilometers per hour means. When you're going miles per hour, 60 miles per hour means in 1 hour, you will travel 60 miles. So you ask yourself, am I going to travel a lot of meters in 1 hour or very few meters in 1 hour? Well, in 1 hour, I'm going to travel a lot of meters. There's a lot of meters in a kilometer. So I need a bigger number. So I multiply by 1,000. Fantastic. We then ask ourselves, in 1 hour, am I going to travel farther in 1 second or not as far in 1 second? So am I going to travel farther in an hour or am I going to travel farther in a second? Hopefully it's obvious. I'm going to travel farther in an hour. So I'm not going to multiply by 3,600. I'm going to divide by 3,600. These unit conversions, you're either making the number bigger or smaller. Just ask yourself what makes sense. Should I get more of it or less of it? So I should travel more meters, but I should travel less of that in 1 second. And so we can kind of check that logic right there. And then the answer is something. Definitely need a calculator for this because it's not just hopping the decimal place. 120 times 1,000. That's nice and simple, but seconds ruins everything. So, such is life. But this is the process you can go through. So you get 33 point, well, the answer was up there all along. 33.33 meters per second. And the very last step is you need to ask yourself, does this answer make sense? And you all probably haven't had this number, 33.33 meters per second, is probably not going to mean anything to you. Like, if you know how fast that is, great. Like, before teaching these classes, I wouldn't have been able to tell you how big that number is. Throughout this class, whenever we're working with units you haven't heard before, like meters per second, I'm going to give you a touch point. That's like something that's like, okay, something that you understand in relation to that. 27 meters per second is 60 miles per hour. So you know what 60 miles per hour is. So whenever you're doing a problem, just remember 27 meters per second is 60 miles per hour. So looking at this, it's a little over 60 miles per hour. Doesn't matter how much, just a little bit. And it's a car. That's very reasonable for a car to go a little over 60 miles per hour. That's kind of roughly this. To that end, if I asked you a problem where I said a person is doing whatever, and you get a final answer of 33 meters per second, you are saying that that person is running at over 60 miles per hour. It's not reasonable. Something is wrong. So again, there's lots of ways to think about your stuff. We're not just working with numbers. We're working with reality. And reality should match what you're used to. You've been living in it for a long time. People can't run over 60 miles per hour. Use that knowledge. So you'll see that as time goes on, I'll make mentions of that and help you give you tips and suggestions for that. But just something to keep in mind. All right. Did I do the whole arrow drawing thing where I had you all? No arrow drawing? Great. All right. What qualities does an arrow have? Let's discover it together. Here's an arrow. You got 30 seconds to look at this arrow. Picture it in your mind because I'm going to erase it and then I'm going to have you tell me how to draw this arrow. So there's an arrow. Picture it. Get all the qualities that you need to know about it in your mind. All right, it's gone. The one thing I'll give you is that I'm going to start here. All right, tell me how to draw that arrow. I need to draw the arrow just like that last one. Tell me what to do.
Draw an angle northeast at roughly 45 degrees.
Ooh. This is the first time someone immediately said the angle of 45 degrees, which is great, but it means I don't get to point out the angle. So the angle is super important. No. That's great. I wanted people to find the angle. If you had just told me draw an arrow up to the right, I would have drawn something like this. That's not the same arrow. By giving me 45 degrees up to the right, that is critical. Otherwise, I have no idea which way this arrow is pointing. If you just tell me up to the right, that's not good enough. This is up to the right. 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 Obviously, all of those aren't the same thing. By giving an angle, we have a very precise measure of where it should point. Now, my question to you, and they also said up to the right. This is 45 degrees with respect to here. This is 45 degrees, well, kind of. This is 45 degrees with respect to here. It not only matters 45 degrees, it also matters with respect to, and generally we say the positive x-axis. All right, great. Is that the same arrow? No. What do I need? All right, give me more information. I believe in you all. What do I need to do to fix this? All right, fix the size. How big should it be? Under the words. All right, how's it look? Very good, right? To that end, there is two things you all needed to tell me. You needed to tell me the direction of it by an angle, and you all needed to tell me how big the arrow was. Ta-da, you discovered vectors. That's what a vector is. It is something with a size and a direction. All right, I'm traveling 30 miles per hour. How long is it going to take me to get to Tampa? Holler out what you think. 6, 7 hours. What else? Or some other ideas? Where in Tampa? That's a good point. Let's say downtown Tampa. Anyone disagree on the 6 to 7 hours? What if I was traveling north? Am I going to get to Tampa? No. We assume the direction. If I was traveling the opposite direction of Tampa, actually, if I'm traveling north, I will never get to Tampa. You know, at best, you'll wrap around the earth and end up back where you started. Direction matters. If you don't tell me the direction, there's certain quantities that, like velocity, if you don't tell me the direction, I don't know which way it's going. And it's a big difference between whether your car is in drive or reverse. So, direction is very important for a lot of things in physics. It makes a big difference which way I push this desk. If I push this desk if I say I'm going to push this desk with a force of 100 newtons, you have no idea what this desk is going to do. You know it's probably going to move, but the people in the front row are going to be far more concerned if I tell them I'm pushing it at them than at the wall. Direction matters, and so we have to account for that. So that's why we use vectors. Vectors are a way of representing measurements. It tells you how big it is. It tells you the direction. It's great. It's such a simple representation that gives you everything you need. The bigger the arrow, the larger the quantity. And the direction is based on the angle. So, vectors, they have magnitude and direction. From Despicable Me, now you know what it means. Magnitude is how big it is. Direction is which way it's pointed. We measure the direction with an angle, generally with respect to the positive x-axis. That's kind of the standard. And then how big it is kind of arbitrary, but once you define how big one arrow is, every other arrow is measured with respect to that one. So, for example, if this arrow was, let's say it's measuring distance. Let's say it's 10 meters. If I draw another arrow and it's 13 meters, it better be bigger than that arrow. Your arrow's size should correspond and make sense. If I had an arrow that was 5 meters, it should be smaller than that. So on and so forth. Great way to visualize what's going to happen. We're going to use it in all sorts of cases. We're going to do it a bunch today. That's pretty much the rest of class is just working with arrows. Now, I'll give you all the... let's see. Yeah. The thing with arrows, though, is we can't work... This is where the triangles are going to come in. Great, there's an arrow. The problem with this is, say I give you 2 arrows. Say I give you an arrow pointed, I say, you travel 5 meters at an angle of 30 degrees, and then you travel, let's make it really easy. Then you travel 6 meters straight up. And my question to you is, how far away am I from where I started? Really simple question. You can see the picture here. How far am I from where I started? The answer is not 11. We can't just add 5 and 6. Why? It would only be 11 if they lined up with each other. They don't. So this is where the unfortunate trigonometry comes in, and there's no getting around this. You can't just add these as is. You can only add arrows that line up with each other, either the same direction or anti-parallel. That's just how it works. Makes sense, right? If I gave you a problem like this, I go 5 meters to the right, and then I go 6 meters to the right again. Easy. It's 11 meters away. Hopefully that's fairly obvious here. Or if I said I went 5 meters to the right, and then I went 6 meters to the left, hopefully you could also tell me what this green arrow is here as well. In this case, it's 11 meters. In this case, it's 1 meter. Hopefully that makes sense. We can't do that when they're not lined up with each other. So we have to break them into pieces that line up with each other. We call this in physics breaking them into components. And to do so, we generally, pretty much always, break them into the x and y components. We break them into the parts that line up with an xy axis because it's just nice and convenient. It's straightforward. So I'm going to show you all this, and don't worry, you're going to get lots of practice. We're going to take this first arrow here, and we're going to find how much it points to the right. We're going to then take this same one, and we're going to figure out how much it points up. And ta-da, it's a right triangle. We can figure out how much it points to the right. We can figure out how much it points up because it's a right triangle. And we're hopefully SOHCAHTOA, and again, we're going to practice that and all that good stuff. So if I called this vector, just to make this a little bit more clear, if I called this like vector A and I called this vector B, just to distinguish them. The way we denote vectors, we put a little arrow above them because they're vectors. Vectors are arrows. This side on the bottom, this is the notation we're going to use. We're going to call this AX. A because it's part of A, X because it's the left-right part of it. We're then going to call this side AY. These little subscripts we're going to use a lot in this class. Think of them like adjectives. The X here is the X component of A, the X part of A. The Y here is the Y component of A. These subscripts can get a little crazy. For example, at some point, I'm going to teach you V is for velocity. And at some point, we're going to have multiple objects. So I need to tell you the velocity of each object. So say I have two objects. I'll say the velocity of object 1. But then its velocity changes over time. There's a beginning and an end. So I'll tell you it's the velocity of object 1 initially. And then I'll tell you it's the velocity of object 1 initially in the X direction. And this is kind of the worst case in this class where we'll have 3 subscripts. They're adjectives. So that's the worst case. That's a foreshadowing. It's a notation thing we do. It's very nice and compact. But just be prepared for that. And that's what we're going to see a lot in this class. So, great. I have AX. I have AY. B, we're very blessed. B has no X component or Y. You can't turn that one into a triangle. It's a straight line pointed up. Good luck making a straight line pointed up into a triangle. So the end result here is if I ask you how far this is, and this is something we're going to practice. If you want to figure out how far you go, you're going to add these components, the X components together. You're going to add the Y components together. So in this case, we'd have to do some math and we'll see that. But for now, I'm just showing you it. That would give you the total X and the total Y. You'd be like, oh my goodness, X and Y. What is going on there? Ta-da, there's a secret third try. This is the final result. This is where you're located. And when you do all this math, you end up finding the X component. Let's just call it C. You end up making a new triangle. And this is what we're going to practice today. So if this doesn't make sense, don't worry. We're going to practice it. But this is why we're going to have to break things into components. That's why I wanted to show you all this before we start getting into the details. You're going to be making triangles, y'all. Lots of triangles. And generally, if you can't make the right triangle, if you can't draw the picture, the rest goes south. So it's a skill that we're going to be working on today. It might roll a little bit into Monday. But it's so important. We can't do physics without that. And it's not like I'm going to teach you all these skills and then say, oh, there's a shortcut way. There is no shortcut. This is the way. It's unfortunate. It's got some process, but it is what it is. All right, vector notation. So before we get into doing the math, more notation stuff. This is how we express it mathematically. So if I have a vector here, vector A, this here, so the I represents, and I'm going to check the stream because I'm always worried that the thing shuts down. The I tells you how much it points to the right or left. I is the X part. So anytime you all see this I hat, it's the same as X. So this says I have a vector that's pointed 8.66 to the right, plus J is the up and down. That's the Y. That's how much it points up, down. So this compact little notation ultimately says I have an arrow, and this is positive. Do y'all want positive to be to the right or to the left? To the right, great. We're all in agreement. That's what everyone goes with. That's what it should be. To the right is positive, to the left is negative. Up is positive, down is negative. So I go to the right, 8.66, then I go up 5, and so vector A is neither of these arrows. Vector A is the hypotenuse. It's the side of it. It is an arrow that points 8.66 to the right, and it points 5 up, and that green arrow is an arrow that points 8.66 to the right and 5 up. And this is how we can kind of express that. So just to clarify, this is the X component of it. This is the Y component of it. And then this side here, we put these that's the magnitude of it. And now that I've kind of drawn this, I'll give you all a few moments. Figure out the value of A. See if y'all remember how to do that. This is something you have learned in your life. I give you that as an encouragement, not as an insult. I'll make it into a question. If A is this, find all right, so this is what this question would look like if I gave it on a quiz or something like that. It's always good to kind of see that. Is the answer... Let me actually figure out what the answer is, and then we figure out a bunch of wrong answers. Is the answer 7.07? $99.996. $10 or 3 points. All right, great. So again, it's one thing for me to ask a question. It's another thing for me to understand if it's actually making sense. So that's why I use this system. I think y'all know how to do this. So let me know the guess. I can get some information from y'all. All right, I'll give you all like 10 more seconds. This is one of those, if you know what to do, it's pretty simple. I say simple. You will need a calculator for this. All right, and I'll close this one in 10 seconds. In 5, 4, 3, 2, 1. All right, so there's a couple of things we can do before we even start answering this question. Before we do any math and actually show you how to do this, we can actually rule out 3 of the answers. So, it's a triangle. We're finding the hypotenuse. One of the things you all should, and you can see this from the picture, the hypotenuse is always the biggest side. Always. This is a really helpful thing to remember when you all are doing this on things. The hypotenuse is always the biggest side, so that already rules out these two. 7 is smaller than 8. That can't be the answer. 3 is smaller than 8. That can't be the answer. It needs to be bigger, all right? And then the next thing is we just look at the size of our arrow, and 99 is very unreasonably large based on our picture. Again, all the arrows should actually like correspond to each other. An arrow of size 99 would be something about that big relative to the other arrows. So great, we ruled that one out. And these are the skills you can use to check your work and things like that. So great. How do we actually get the answer? How do we actually get that? Yeah.
Pythagorean theorem.
Pythagorean theorem. That's right. It's the triangle with 2 sides. So if you want to find the hypotenuse, remember y'all, a squared plus b squared equals c squared. If you don't remember it, I hope that rings a bell. If not, you need to know this. We're solving for c, so it's the square root of a squared plus b squared, which equals the square root of 8.66 squared plus 5 squared. It comes out to roughly 10, 9.999. I'm just going to go ahead and round that. And boom. So this is where I actually point out the answer. But good. I'm glad to see the answers are different because this gives me feedback. So this is something, just remember back, this is something you're going to be doing a lot. And it's okay. Notice every time I do this, it doesn't show who people are. I never go and look at who put what response. So never feel embarrassed. No one's going to know what you put for these. It is better to get this wrong now and learn it than on a test. So never feel bad about missing a problem here because it changes absolutely nothing in life. Hopefully it actually changes things for the better if you learn from it. But yeah, we're just finding the third side of a triangle. And this is something we're going to do a bunch in this class. When you have two sides, Pythagorean theorem finds the third. All right. So, yeah, I want y'all to practice this. Try to draw these two arrows. I'm going to call them A and I'm going to call them B. Vector A is negative 3 I hat plus 6 j hat. B is 7 I hat minus 1.5 j hat. Go ahead and try it out. And remember, the final answer is ultimately just a single arrow. So A will be a single arrow. You'll draw some other arrows to get there, but A is one arrow and B is one arrow, and we just draw the sides of it to get the final result. All right, so I'll draw the answer for A, and then I'll give you a few moments to see if you can figure out why that is, if you're unsure. That's A. And I'll show you how I drew that. I did some things in my head. So to draw A, what did I do? I secretly in my head, negative 3 I hat means negative, it's 3 in the x direction. If you think it's negative, what direction do you think that is? Left or right? Left, that's right. So we're going to draw an arrow. We're going to draw a line down here, and we're going to point it to the left. Fantastic. All right, positive 6, j hat, that's going to be up. And ta-da, all I then did is I drew something from the beginning to the end, and there's my answer. It's more up than to the left. 6 is a bigger number than 3, so I made it point steeper. And that corresponds to this picture. Now, the nice thing with addition is the order doesn't matter. So if instead you decided to go up 6 and then over 3, you get the exact same result. 2 plus 3 is the same as 3 plus 2. And what you are secretly doing when you're drawing this picture is you're adding vectors. On a later slide, this is called the tip-to-tail method. You draw one vector, and then right where that vector is, you draw the next one, and that's how you add vectors visually. I'll have a separate slide for that you secretly did that when doing this. Yeah?
Would I be wrong if I put the head of the arrow the other way?
That's a great question. So what if instead, so we have this line here, and we instead put it here. And so the key to this is our vector A should match its components. It should match the components. So to that end, negative 3 means my x is pointed to the left. If I point it this way, is it pointed to the left or to the right? So it's the wrong direction. And then we also can check the y component. This is positive, so it needs to point up, whereas in this case, it's pointed down. Now, I'm glad you asked that because that is a really good question. How do I pick the direction of the arrows? They should match the components. They should all match up. So this arrow is pointed up to the left. My x component's to the left. My y component is up. They all match. Life is good. And this is also a really good point. If I wanted to draw negative A, so if I wanted to draw the vector negative A, it is exactly the opposite. It is the opposite. So negative A would point the other way. Because instead of left, now it's right. Instead of up, now it's down. By putting a negative inside, it flips. Negative A turns this to a positive 3. Negative A turns this to a negative 6. So a negative vector is just the same vector flip. And we're going to use that when we add vector, when we actually subtract vectors. Subtraction is just adding a negative. So we'll see that later. Anyway, the answer to B is going to be 7 to the right and 1.5 down. So again, this is the final result. This is vector B. How did I get there? I went 7 to the right and I went 1.5 down. And I just went from the beginning to the end. All right. So there's that. 7 and 1.5, and I think I'll revisit these in a second. Okay, so great. We got vector, says A, but it should be B, based on the last slide. Boop. Here's the one. I'll even copy the picture over. I'm going to have you all try this out. What is the magnitude of B? So this is the thing I had you all do before. And what is the angle of B with respect to the x-axis? The positive x-axis. So spend a few moments, see if you can figure out how to do this. And when I'm saying the angle, I'll even show you all. The angle I'm talking about is this angle. Remember, the positive x-axis points this way. So it's the angle with respect to that, which ends up being inside our triangle. I'm going to put the answer here simply so you can check your work. You cannot get this answer without doing it correctly. I'll hold off on the second one because I want to make a point there. Yeah. Yeah, that was actually the thing I was holding on. Yes, so actually the answer here, and the answer is a negative angle, or, and I'll talk about this now since you asked the question. Negative 12.09 degrees, or you can write it this way, 12.09 degrees below the x-axis. A negative angle means you're measuring. So I don't know if I think you all saw the unit circle. That was something at some point. So if y'all remember your unit circle, angles are measured counterclockwise. That's like the standard. I don't know why. That's what someone decided at some point. So a positive angle generally means you're going counterclockwise. A negative angle is measured clockwise. That's just the standardized way of doing it. Not sure who decided that. So in this case, because we're below it, you either would say it's negative 12.09 degrees, or you would say it's 12.09 degrees below the x-axis. So let me show you all how to get these values. The magnitude, hopefully that sounds, remember it's just the components, or it's just the hypotenuse. The magnitude of B is going to be the square root of 7 squared plus negative 1.5 squared. And when you do that, you get 7.16. To get this angle, SOHCAHTOA. If you all don't know this phrase, it is going to be very important to you. SOHCAHTOA helps us know the relationship between sides of a triangle and the angle. Sine of theta equals opposite over hypotenuse. Cosine of theta equals adjacent over hypotenuse. Tangent of theta equals opposite over adjacent. And you just decide, what do I have? What do I need? In this case, I need the theta. Again, it's what's given. What am I solving for? In this case, I have two sides of a triangle, and I have the angle. So the question is, what sides do I have? Well, the angle I want is here. So this is my opposite side, and this is my adjacent side. Opposite's the one opposite, adjacent's the one next to it. So we have opposite and adjacent. We want the angle, so we're going to choose tangent. Now, when you do this angle stuff, don't put negatives in there. You will see examples of this. If you have an example, like for example, if you have an arrow pointed up to the left, just don't put negatives in. Only put positives in. And then based on your picture, decide that it's negative. Use the picture to show you that it's negative. If I instead had given you one that was like negative 7 I hat plus 1.5 j hat, it doesn't work out. And I don't know if I have the time for it, but just trust me on this for now, for the sake of time. Trust me, do not put negatives when you're doing this. Use the picture to do this. All right, now, to get this angle, this is where I told you all, make certain you have a calculator that you're comfortable with and familiar with. Don't use a phone calculator. because you need to know where these buttons are on your calculator. You need to know where the tangent inverse button is on your calculator. It's different on every single one. It's very often right above the tangent. Tangent inverse is the opposite of tan. Make certain your calculator is in degrees mode. That's another setting that you sometimes have to fiddle with. My calculator was in radians mode when I plugged this in, and I got an angle of 0.211. I look at that and say, that's not a reasonable number, because that angle is not 0.211 degrees. That's like a tiny, tiny angle. I said, oh, it's in radians. It's one of those subtle things you got to be careful of. So there you go, that. But the reality is we're going to call it negative because it's below the x-axis, okay? Because you can imagine here, if I said, what's the angle? How far away is it? If I just told you it's 12.09 degrees, you have two options, above or below. Positive is above, negative is below. If we're not clear in our wording, if we're not clear in our notation, then people can't understand you. And that's why we have to be very clear in these that's why there's these standard way of doing things. So precision is important when it comes to math and science. Very, very important. All right. So there you go. Trigonometry. You're going to have to do it. Now, so we're going to skip this. We're going to skip this. For the sake of time, I want to jump down to adding vectors visually. And this is we'll do this, and then I'll show you how to do it numerically. We've already done this. I already made mention of it. If you have any two arrows, I don't care which ones. Here's two arrows. To add them, you just draw one of the arrows, and then you start drawing the next arrow right where the first one ended. So in this case, I got two arrows down here. I want to add them because I decided I want to. So I draw R1. I then draw R2. All I did was draw R2. It's not the perfect drawing. You do not need to bring a protractor to the exams or anything like that. You just need them to be roughly correct. I'm not going to give you answers on a test that are really similar to each other. A good rule of thumb is if you're within 1 to 2% of my answer, you're good. Because that always comes up. People get slightly different answers. 1 to 2% means it's just rounding, and I'm happy because that means you did the right process. Okay, so what's the final result? We start at the beginning, and we draw this, and ta-da, that's R1 plus R2. And again, addition, the order doesn't matter. What if instead you wanted to draw R1 first? Or R2 first? So this is R1 plus R2. What if instead you said, you're going to draw R2, and then you're going to draw R1. Oh, look, you get to the same exact spot. 3 plus 2 is the same as 2 plus 3. Order doesn't matter. So this is a very, very useful skill. It lets you check your work. It lets you make certain things make sense. It lets you make predictions on what's going to happen. All that good stuff. It gives you a sense of what's going to happen. It's not precise. Again, I'm not using a protractor here. I'm not using a ruler. But it does give me a sense that if I add these two, I'm going to get something that points roughly up and to the right. All right, try it out. Here's two vectors. A points down and to the right with an angle of 45 degrees below the x-axis. B points up and to the right with an angle of 45 degrees with respect to the positive x-axis. Add them together. What's A plus B look like? Draw them out. There's no reason to try to do it in your head because drawing it out takes 5 seconds and it's way less likely you'll make a mistake. All right, give you all like 20 more seconds. There's no math involved here. And these are the kind of questions that'll make up some of the test. They're questions that don't involve any math, but they're basically, do you know what's going, like, I call them conceptual questions. No math involved, just going through some process. All right, I'll close this out in 5, 4, 3, 2, 1. Oop. All right, and remember the order that I add these doesn't matter. So I asked you to do A plus B, but just to keep things interesting, let's do B plus A. So I draw B, I draw A, the final result, there it is. If you instead decide to do A plus B, there's A, there's B, there's A plus B. It still points to the right. Ta-da! And so, something I want to point out here that this is secretly doing, remember I told you all breaking things into components, you can only add things to components, yada yada. All right, which way does A point, up or down? Down. Which way does B point? Up. So the part of A that points up and the part of B that points down cancel each other out. So it is adding the components together. The part of A that points down and the part of B that points up, this one points up the same amount, this one points down, so they cancel each other out. They both point to the right, so you get a bigger arrow to the right. So that's what's going on here. It is adding the components visually. It's very nice. Now, the next thing I want to show you all is how to subtract vectors. So, same question. I'm just going to erase some things because the answer is going to be different. I'll go ahead and tell you that now. So, there's A, there's B. Which vector below represents A minus B? Now, there's one thing I got to tell you for this. So, all these got shifted for some weird reason, but there you go. That goes with that. That goes with that. So, I'm going to give you all a hint here before I send it to y'all. Hint. A minus B is the same thing as A plus negative B. If you know how to add, we can use the same ideas. We just got to turn a subtraction problem into an addition problem. That's how. And then the only other thing you need to know, and I mentioned this before, but I'm going to remind you all of it. Negative B is just B but backwards. A negative vector, everything gets flipped. So you just put the arrowhead on the other side. All right. I'm really curious if I hit start, is it the same question? It is the same question. Okay. That's good for me to know. All right. Woo. All right. So try it out. What is A plus negative B? i.e. A minus B. And feel free during these to check with the people around you. Remember, if you all have different there's only one right answer. All these arrows are different. If you have a different answer than someone, one of you is wrong or both of you is wrong. Like, that's always going to be true in this class. There is every now and then a question that has multiple right answers, and I might give you some warning on that. Generally, though, they only have one right answer. All right, so 5 more seconds. So 5, 4, 3, 2, 1. All right, so again, before I even draw what this looks like, we can do some little tricks. Which way does A point? Points down. Which way does B point? Great, so those parts are going to add together. Does A point to the right or left? Right, B points left. In this case, that amount is the same, so they cancel each other. It's not always going to cancel. These only cancel because how much this one points to the right and how much this one points to the left and how much this one points to the right are the same amount. But that's, you're secretly doing the math kind of behind the scene. But yeah, if we just draw them, there's A, there's B, the final result. So that's A plus negative B, which is the exact same thing as A minus B, which is the exact same thing as negative B plus A, however many ways you want to write that. They're all the same. There you go. It's down. And so this is the thing that we're going to continue to practice throughout all, you're going to see so much of vector addition. But great. We know how to do it visually. This is fantastic because it gives us a sense of what the right answer is. We need precision, though, and we're going to have to do some math because it's one thing to know an arrow points down. It's another thing to know an arrow points down 10.23. So as a doctor, it's one thing to say someone has a high blood pressure. It's another thing to actually give the number for that blood pressure. I don't know what high blood pressure is, otherwise I'd give you a number. So that's numbers matter. Precision matters. In a lot of cases, if you have a sense of what's going to happen, that's good enough. But when you're working with things that matter a lot, you need precision so that you know exactly what's going to happen. So we have to do the math. That's why we do math in this class, is it gives us precision. It gives us an exact amount of what we can expect. And yeah, as a doctor, that's something you need to know. As engineers, it's something they need to know. Numbers exist for a reason. They're the language of logic, and without them, you can't be precise. So we're going to learn how to add them numerically, and it's going to be breaking them into components. So I'm going to show you all that with a picture first, and then we'll do one example, and then we'll see how much more. You know what? We'll actually be able to do this example, I think. I'll work through this as the example. So here's two vectors, A and B. Here's them added together graphically, the way you've been doing it. You got A, you put B next, you put an arrow from the beginning to the end, and life is good. Now, if I actually want to figure out how big R is, I have to break. So I'll draw it out here, and then you'll see it in the next slide. I have to make a bunch of triangles. I have to break A into its components. And then I have to break B into its components, i.e. turn it into a right triangle. If you cannot draw the right triangle, you cannot solve the problem. So great, I got the x and y components of A, I got the x and y components of B, and now you can see if I add AX and BX, I get the total x. If I add AY and BY, I get the total y. So when I add those together, so this side here, let's call it RX, that's going to equal AX plus BX. In fact, I'll put it right here. How do I get RY? I'm going to add AY plus BY. Now, it's all addition here. Just remember, if you're pointed up, it's positive. If you're pointed down, it's negative. If you're pointed right, it's positive. If you're pointed left, it's negative. In this case, they're all positive, but that's not always going to be the case. You'll see that in the example I give. Great. That'll give us Rx and Ry. But if I actually want to figure out how big R is, there's one last step. The magnitude of R, that's how big this thing is the square root of that. So this is a three-step process. Break the vectors into X and Y. Combine the X's, combine the Y's, and at the very end, you can recombine them all together with Pythagorean's theorem. Yes, it takes a little bit of time. There is no shortcuts. There is no shortcuts I know of to do this quicker. It's just what you have to do. It's one of those things. It is what it is. And this is something that we're covering now because you're going to be doing it with velocities, with forces, with momentums. You'll see. It'll be a good time. We got a couple weeks until it's going to show up with things, but I want to prepare you all now because it's such an important skill. And if my picture's real messy, the next one is, a bit nicer. It's the same thing, but it's not with my messy handwriting. So, woo. All right. So this is the problem that I'll then solve in the next 6 minutes. So this is an example. When we get to forces, this is the kind of stuff we're going to do. So I got a boat pulling up and to the left. So it's pulling with 5,000 units of force. We're going to learn eventually those units are called newtons, but for now I just put the word units here because I have to take a problem. So 5,000 units of force with an angle of 12 degrees with respect to the vertical, to the left of it. And then I got 4,000 units of force, 15 degrees to the right of the vertical. The question is, what is the total force? The net force, so the word net here means total. You're going to see that word a bunch in this class. Net means total. It means add these two together. So if I called this vector A and I call this vector B. This question is saying, what is A plus B? And so the first thing I want you all to spend a few seconds. Can you draw the correct right triangles? Remember, the first step is to break these into X and Y's. Can you do it? Try it out. And you generally want to try to draw the triangle such that it includes the angles that are given. If possible, that's ideal. So like I'll show you, for example, you could draw a right triangle here. And that is not incorrect. That's fine. You would just have to recognize that this angle is 12 degrees using, I don't know what the name of that theorem is, but opposite interior angles or something like that. We're going to use tricks like that in future things, but if possible, draw a right triangle using the angle that's given because it makes your life a little bit easier. So if this is A, this would be my AY, and this would be my AX. Unfortunately, it's very difficult to draw both A and B on this picture. So I'm just going to go ahead and draw A off here to the right. So this is vector A. We're going to draw an arrow up and an arrow to the right. Now, again, the question I always get, so great, I turned it into a right triangle. The question is, should that arrow on the right side be up or down? It's a really simple question when you know, it's a simple thing to answer when you know the right question to ask yourself. You just ask yourself, does this arrow point up or down? Y'all tell me. Is it up or is it down? Up. So this arrow is going to point up. Does this arrow point to the left or to the right? Left. So then my x component should point to the left. That's all the question you have to ask yourself. So the y component points up because the arrow points up. The x component points to the left because the arrow points to the left. And that's how you decide the direction. If you don't put these arrows, you're going to get the problem wrong. You'll see what I mean in a second. So I got 2 minutes. We'll see if I can actually get through this whole thing. Probably not. But I can at least do this first one and then leave the second one for you all. So great. We're going to find AY. We're going to find AX. This angle is 12 degrees. So this is where you have to remember SOHCAHTOA. You have the hypotenuse. You have the angle. Let's do the X component. I'll give you all 10 seconds. Which one are you going to want to use? SOHCAH, or sine, cosine, or tangent? You don't need to say it out. Just think it in your head. Which one will let us find the X component? And the answer is going to be sine, because this is the opposite side. So sine of theta equals opposite over hypotenuse. So sine of 12 degrees is going to equal AX, because that's my opposite, over 5,000. To solve for AX, you just multiply the 5,000 over. So you get 5,000 times sine of 12. And that's going to come out to 1,000 something. I only know that because I've solved this problem 3 times today. I cannot do this in my head. Oh, yeah, my calculator decided to go to approximate mode. So when I put it in there, there we go. 1,039.56. And there's a very subtle thing here. If you say that that's the X component, it's wrong. What is it missing? See if anyone knows. Which way is this arrow pointed? Left or right? It's negative. The math doesn't tell you that. The picture does. If you don't put that negative, when you combine it with the other one, you're going to get the wrong answer. So, obviously we're out of time. This problem I have solved out. So I encourage you all to try this one. I will actually upload the PowerPoints with the full worked out solution to this, and I'll quickly go over it on Tuesday. But this is a great problem that applies all the vector stuff. Components, adding them together. All the steps are in this one problem. This is one of the last ones in the problem set for this week because it's got the most challenge to it. So, have a good weekend, y'all. Good luck. I'll hang around. And yeah, next week we'll get into kinematics.
So, since we're not